Let's start our next session on general vector spaces, and we will see more examples and non-examples for subspaces of different vector spaces. So the first one is, we know that what is meant by subspace. A subset W of a vector space V is called a subspace of V if W is itself a vector space under the addition and scalar multiplication defined on V, and W is a subspace of V if and only if it is closed under addition and scalar multiplication. There is no need to check all the axioms, we just need to check whether axiom 1 holds and axiom 6 holds. Now we have seen which are the subspaces of R2. The zero subspace, R2 itself, and any line passing through origin will be a subspace of R2, and here we will see a subset of R2 which is not a subspace. So I am taking W as the set of all points ordered pair xy in R2 with x greater than or equal to 0 and y greater than or equal to 0. So geometrically, if x is greater than or equal to 0 and y is greater than or equal to 0, we will be in the first quadrant or in the positive x-axis or positive y-axis. So this is our region under consideration. This is not a subspace of R2 because it is not closed under scalar multiplication. For example, suppose this is the point 1 1, so we have ordered pair 1 1 here. If we multiply ordered pair 1 1 with minus 1, we will get ordered pair minus 1, and it will be here in the third quadrant. It is not in the first quadrant. So this set is not closed under scalar multiplication. Okay. Hence it will not form a subspace of R2. And the next one is, we see some subspaces of MNN. I hope you remember what is meant by MNN. This forms set of all matrix of size n by n where each entries are from R. We proved that this forms a vector space with coordinate wise addition and scalar multiplication. And now I am considering a subset of MNN which consists of all symmetric n by n matrices. All the n cross n by n matrices which are symmetric. Symmetric means A transpose equal to A itself. We are considering all such matrices. The sum of two symmetric n by n matrices is a symmetric matrix, and any scalar multiple of a symmetric n by n matrix is also symmetric. Thus, the set of all symmetric n by n matrices is closed under addition and scalar multiplication, and hence it is a subspace of MNN. So suppose I will explain it in 2 by 2 matrices of size 2 by 2. Suppose A, B, B, C. This is a symmetric matrix. And another one is X, Y, Y, Z. If we add them together, we will get A plus X, B plus Y, then B plus Y, C plus Z. It's easy to see that this is also a symmetric matrix. So sum of two symmetric matrices are again a symmetric matrix, And if we multiply this a, b, b, c with a scalar, with some scalar k, we will get ka, kb, kb and kc. This is again a symmetric matrix. So the collection of all 2 by 2 symmetric matrices, or in general the collection of all n by n symmetric matrices are closed under addition as well as scalar multiplication, and hence it is a subspace of Mn. Okay, now we will see some more examples for Mn. The set of all upper triangular matrices. Upper triangular matrices means, suppose we have an n by n matrix, and here you will have diagonal entries, and any entry below the diagonal is 0. Any entry below the diagonal is 0. Such matrices are known as upper triangular matrices. If you add two upper triangular matrices, you will get another upper triangular matrix. If you multiply an upper triangular matrix with some scalar k, still you will get an upper triangular matrix. Similarly, there are lower triangular matrices. The collection of all lower triangular matrices. Lower triangular matrix means a matrix of the form, this is an n by n matrix, and here we have the diagonals. Lower triangular means anything above the diagonal is 0. For example, if we have a 3 by 3 matrix, say 1 0 0 2 3 0 4 5 6, these are the diagonal entries, and anything above the diagonal is 0. So this is a lower triangular matrix. And it's easy to see that if you add two lower triangular matrices, you will get another lower triangular matrix. And if you multiply a lower triangular matrix with some scalar k, again you will get a lower triangular matrix. So the collection of all lower triangular n by n matrices is closed under addition as well as scalar multiplication. Hence, it is a subspace of Mn. Now the next one is set of all diagonal matrices. Only the diagonal entries can be non-zero. Anything other than diagonal entry is 0. Such matrices are known as diagonal matrices. If you add two diagonal matrices, you will get another diagonal matrix. And if you multiply a diagonal matrix with a scalar k, still you will get a diagonal matrix. So the collection of all diagonal n by n matrices forms a vector subspace of Mn, since it is closed under addition and scalar multiplication. So these are all subspaces of Mn. Set of all symmetric matrices, set of all upper triangular matrices, set of all lower triangular matrices, set of all diagonal matrices are all subspaces of Mn. Now we will see a subset of Mn that is not a subspace. We are taking W as the set of all invertible n by n matrices. This will not be a subspace of Mn, for it is not closed under addition and not closed under scalar multiplication. One easy example is that take In, the 1 in the diagonal entries and zeros elsewhere. This is an invertible matrix. And the next one is minus In. I am taking another one, minus 1 in the diagonal positions and zeros elsewhere. These two are invertible matrices, but their sum will be the zero matrix, which is not invertible. We will see one example here. Consider matrices U equal to 1, 2, 2, 5 and V equal to -1, 2, -2, 5. So these are invertible matrices because the determinant of the first matrix U is 5 minus 4, which is equal to 1, not equal to 0. So the determinant is not equal to 0 means the matrix is invertible. Similarly, here also the determinant is non-zero, therefore V is also an invertible matrix. But if we add them, we will get, or here U plus V will be 0, 0, 4, 10. So the first column is entirely 0. Therefore, this matrix is not an invertible one. So it is not closed under addition. And similarly, if we multiply this U with 0, the scalar 0, we will get the 0 matrix, which is not invertible. Okay. Therefore, the set of all invertible n by n matrices does not they will not satisfy the closure property for vector addition as well as scalar multiplication. Therefore, this W is not a subspace of M and N. Now we will see another vector space. We have discussed F minus infinity, infinity. Set of all functions from minus infinity, infinity to R. And we proved that this forms a vector space under the pointwise addition of functions as well as pointwise scalar multiplication. K f of x is equal to k times f of x. Now we will see some subspaces of this. We know that the sum of two continuous functions is continuous, and a constant times a continuous function is continuous. Suppose f and g are two continuous functions, then f plus g is a continuous function. If you multiply a continuous function f with a constant c, then cf is also a continuous function. So we can say that the set of all continuous functions on minus infinity, infinity is closed under vector addition and it is closed under scalar multiplication. Therefore, this will form a subspace of f minus infinity, infinity. And we will denote this, this subspace by c minus infinity, infinity. So what is meant by c minus infinity, infinity? This is equal to set of all functions from open interval minus infinity, infinity to the set of all real numbers such that f is continuous on minus infinity, infinity. So this forms a subspace of set of all functions from minus infinity, infinity to R. Now another example for a subspace of f minus infinity, infinity is functions with continuous derivatives. A function with continuous derivative is said to be continuously differentiable. Function with continuous derivative means, suppose f is a function from minus infinity to infinity to R, and the function f dash, f prime from minus infinity, infinity to R is continuous. The first derivative of f prime is continuous on the entire real line open interval minus infinity, infinity. Then we say that f is a function with continuous derivative. Such functions are said to be continuously differentiable. And if f and g are two continuously differentiable functions, then their sum is also continuously differentiable. So the sum of two continuously differentiable functions is continuously differentiable, and that a constant times a continuously differentiable function is also continuously differentiable. So what we have is, if we take the collection of all continuously differentiable functions, it is closed under vector addition and it is closed under scalar multiplication. Therefore, the functions that are continuously differentiable on minus infinity infinity forms a subspace of f minus infinity infinity. Now, the set of all continuously differentiable functions on minus infinity infinity is denoted by C1 minus infinity infinity, where the superscript 1 emphasizes that the first derivatives are continuous. Now, the set of all functions with m continuous derivatives on open interval minus infinity infinity is also a subspace of f minus infinity infinity. So, what we have is, suppose f is a function from minus infinity infinity to r, and we are considering the first m derivatives of f. So, f prime, f double prime, f triple prime, and so on, fm, the mth derivative of f. These are all functions from minus infinity infinity to r, and these are all continuous functions. Here we are considering such functions. The first m derivatives are continuous. So, the set of all functions with m continuous derivatives on open interval minus infinity infinity is a subspace of f minus infinity infinity, and we will denote this space by Cm minus infinity infinity. Also, the set of all functions with derivatives of all orders on minus infinity infinity is also a subspace of f or f minus infinity infinity. The functions like e power x or sin x, these are all infinitely differentiable. If you differentiate e power x infinitely many times, you will get e power x itself, and sin x can be differentiated infinitely many times. First derivative is cos x, next is minus sin x, then you will get minus cos x, and we can continue this process infinitely many times. So, such functions which are continuously differentiable at infinitely many times. So, the set of all functions with the derivatives of all orders on open interval minus infinity infinity also forms a subspace of set of all functions from minus infinity infinity to r. And this space, continuous infinitely differentiable functions, is denoted by C infinity on minus infinity infinity. Now, we are considering the space of all polynomials. We are considering all the polynomials. It forms a vector space under usual addition. Suppose P and Q are two polynomials, then P plus Q on X is defined as P of X plus Q of X, and a constant times P of X is defined as constant times P of X. With respect to these two operations, the space of all polynomials forms a vector space over the set of all real numbers, and the polynomial is a function that can be expressed in the form P of X is equal to a0 plus a1x plus etc. an x power n. If this an is non-zero, then we say that this polynomial has degree n. Okay, here the coefficients are all constants. The sum of two polynomials is a polynomial, and a constant times a polynomial is also a polynomial. So, the set of all polynomials forms a subspace of set of all functions from minus infinity to R, means f minus infinity. So set of all polynomials forms a subspace of f minus infinity. Also, we will denote this space by p infinity because we are considering all the polynomials. There will be polynomials of degree 1, polynomials of degree 100, polynomials of degree 1000, and polynomials of all degrees are here, so that we will denote the space by p infinity. Now, we are considering another subspace, the subspace of polynomials of degree less than or equal to n. The degree of a polynomial is the highest power of the variable that occurs with a non-zero coefficient. We know that a polynomial of this is of this form: a0 plus a1x plus etc. an x power n. This is a polynomial, and if this an is non-zero, then we say that this polynomial has degree n. If an is 0 but an minus 1 is non-zero, then we say that this polynomial has degree n minus 1, and so on. So, if we take two polynomials of degree n, we are considering polynomials of degree equal to n only, whether it forms a subspace of f minus infinity. For example, suppose I am taking p of x as 1 plus x square. This is a second degree polynomial, and I am considering q of x as minus 1 minus x square. This is also a second degree polynomial. If you add them together, you will get 0, which is a polynomial of degree 0. So, if we add two polynomials of same degree or is a degree equal to n, we may not get a polynomial of degree n. We may or may not get a polynomial of degree n. Anyway, it's not sure, just like in this case. So, we can say that the set of all nth degree polynomials are not closed under addition as well as scalar multiplication, because if you multiply p of x with 0, you will get the 0 polynomial. So, the set of all polynomials with degree equal to n will not be closed under addition as well as scalar multiplication, because it will not be so that it will not be a subspace of f minus infinity. So, here we are taking this is another example: 1 plus 2x plus 3x square and 5 plus 7x minus 3x square. So, when we add them together, plus 3x square minus 3x square will get cancelled. What we have is 6 plus 9x, which is a polynomial of degree 1. So, however, for each non-negative integer n, the polynomials of degree n or less forms a subspace of f of minus infinity, because if you add an nth degree polynomial and a polynomial of degree less than or equal to n, anyway we will not get a polynomial whose degree is greater than n. The degree of the sum will always be less than or equal to n. So, the set of all polynomials of degree less than or equal to n forms a subspace of f minus infinity, and we will denote this space by Pn. Here we consider all constants to be polynomials of degree 0, because we know that a polynomial is of the form p of x is equal to a0 plus a1x plus etc. plus an x power n. Suppose this a1 is 0, a2 is 0, etc. an is 0, and the only one is non-zero is a0. then we say that it is a polynomial of degree 0. Now, remark, polynomials are continuous functions. Okay, therefore we can say that the space of all polynomials, already we know that the space of all polynomials forms a subspace of f minus infinity infinity. At the same time, since polynomials are all continuous functions, we can say that the space of all polynomials is a subspace of c minus infinity infinity. Also, the polynomials have continuous derivatives of all orders on minus infinity infinity. Thus, it follows that P infinity is not only a subspace of f minus infinity infinity, but also it is a subspace of c minus infinity infinity, and it is a subspace of c1 minus infinity infinity. It is a subspace of c2 minus infinity infinity. In general, it is a subspace of cm minus infinity infinity for any natural number m. Also, in the previous examples, we considered functions that were defined at all points of the interval minus infinity infinity. But sometimes we will want to consider functions that are only defined on some sub-intervals of minus infinity infinity, say closed interval AB or open interval AB. In that case, we will use the notations CAB, C closed interval AB for the space of all continuous functions on closed interval AB, and C open AB is the space of all continuous functions on open interval AB. So we will continue our discussions on subspaces in our next class.